Hi, I am Dr. AJ Kumar, PhD. We're reading Artin 2.12. Before we get to that, I have some bullshit announcements that I know everyone loves. Bullshit announcements in the middle of them trying to listen to the content. So, first thing, a couple videos ago, I had a video where I had some handwritten notes in this program over here on the side, and I saved them, and they got saved as a high-resolution image, because what else are they going to get saved as? And I said, okay, well, I'll upload them on my locals board, so anyone who wants can go just get them off my locals board. And I tried to do that, and that was like 2 weeks ago, maybe, and it took down my locals board, and it still has not gone back up. I haven't emailed them to try to figure out or get it fixed. So I guess I don't have a locals board anymore. I guess I could send them an email. I haven't even checked my email. I don't read my email, by the way, so don't send me emails. If you want an email to me, if you want to get in touch with me, the best way is to email zxq9@zxq9.com and just address it to Dr. AJ Kumar, and I'll get the message. Anyway, speaking of which, about in September, this was recorded in September, this was episode 7 of the podcast I have with Canon. Each one has a different title, so depending on what we're talking about, if it's math or Erlang or something like that, it's called Math After Dark, but they're all called SICA. It stands for Structure and Interpretation of Rational Analysis, and I'll let you figure out why it's called that. What was I going to say? Oh, I've started uploading everything from that podcast. Not everything is up yet, to this channel on Rumble called the Craig Cannon Power Hour with Craig Cannon, and in particular from episode 7, which we recorded at the beginning of September. Finally got around to watching it all the way through and making clips, because we literally sit down and talk, and we talk for 6 hours. And so this starts about 3 hours in, so that's why it's part 6. And this turned out, it's 2 hours long, so part 6 of a 6-hour podcast. It ended up being 2 hours long, and it's a very linear conversation. It turned out really, really, really well. And 2 hours, that's a full podcast, really. And I'm really happy with how this turned out. The conversation was so much fun to listen to, even though I was taking part in the conversation. I'm very proud of this, and I thought the thumbnail was really clever. If you get this joke, you know what? I might as well explain it. Should I explain it? I guess you can't. I guess if you don't get it, Okay, I'll explain it. So I'm not going to explain what paper tiger means, but this photo is literally of a paper tiger. And if you look up, there was this species of tiger, I think, is extinct in China now. I don't know much about tigers, and I don't remember the details of the story, but it was something like the Chinese government issued something. Hey, if you can prove that this species of tiger is not extinct, then we'll give you a reward. And so this guy takes this literal paper cutout of a tiger, I guess it's cardboard, but paper. It's literally a paper tiger, puts it into a forest near his house, takes a photo of it, and brings it to the local government. They blast it all over the newspapers, and and then of course people figure out that it's fake. But it tricked the local Chinese officials. And nobody spotted that wasn't real, or it's more that probably everyone understood that it was fake, but in the culture of China, you can't point it out. It's kind of weird. So anyway, we were talking a lot about China, and I thought this was I'm very proud of this thumbnail. Anyway, all of our old podcasts are up here, particularly the WFC ones. These are all up. Yeah, we have one called Everything in China is Fake. If you know this meme. Oh, we talked about this meme we talked about everything in this photo, in the thumbnail. Let's see. Yeah, parts 1 through 4. Parts 1 through 4. Part 4 is actually pretty fun, but part 6 is kind of dull. Or, correction, part 7 is pretty dull. Part 6, I think we really... This How China Works with the Paper Tiger. This one was really, really good. I think this was really the best segment of podcast we've ever done, and they're all pretty good. Anyway, we riff off each other well. Okay, and then I wanted to ask, so I've noticed, I am surprised that literally anybody is watching these videos. And they're particularly getting but greater than 0 traction on Rumble. And I am wondering, I'd like to hear from you guys. I want to know, 55 of you watched this 2-hour-long video of literally just me reading a textbook. So I would like to hear from you guys. Then, the last thing I wanted to talk about was, I have an Odyssey and I haven't put anything up there yet, just cause I already have way too many fucking platforms to deal with, and but I did look at Odyssey and it looks like a much more interesting concept than either BitChute or Rumble. Odyssey seems to be much closer to what I have in mind with Marketplace. Anyway, what was I going to say? I still can't quite figure out how it works. It has some weird, stupid... this weird thing where it has some shit coin that it operates on, and I guess it seems like an interesting concept. The problem with anything with crypto is so it works based off of some crypto thing, and I went, oh look, I have all of this crypto, and I went to receive. Oh, oops. I wanted to cash out, basically. I wanted to figure out. No. I went to buy it, and I put United States in here. This country isn't supported yet. Really? Okay. So, anyway, but the video hosting aspect of it seems to work. So anyway, what was I originally up on? I originally had... I was testing the paywalling feature, with this clip from one of the old podcasts. This was, I think, from the WFC one. Anyway, what was I going to say about this? Boy, if I can't remember, if I have that poor of short-term memory, this reading episode's going to go poorly. Oh, I remember. So one concern I have with doing this reading playlist, I don't think I'm going to get into trouble, but I guess I'm technically probably violating some copyright stuff. The logic I had in my head is so much of, YouTube videos and, shitty content on the internet is reaction videos. And if reaction videos are okay, then certainly this is okay. This is way higher tier and much closer to fair use than reaction materials. It's clearly transformative. It's not a substitute. It's in no way a substitute for the original product. I'm constantly telling people to go buy it. By the way, go buy the book. So I think kind of the ultimate question in this is, am I increasing the value of the copyrighted material or decreasing its market value? And if I am providing a complementary product and not a substitute, I'm also not really doing this for profit. The videos on Rumble are monetized, and the only reason I do, if I could, I can let me explain. Here, if I go to upload a video on Rumble, okay, and I'm just gonna pick some shitty clip. Here, I'm gonna pick the Negra Swans clip, okay? Okay, and I'm just gonna upload this. Okay, and I'm not going to upload it to any channel. I'm and I'm going to click upload. And I have these 4 options. I don't understand what these 2 are. I guess it's where they upload. I have no idea. I always pick Rumble only, and then it's monetized. If I pick... Fucking mouse. Is the mouse dead? Yes, it is. Let me put it on the charger. Okay. If I pick personal use, great, it's not monetized. It's also not searchable, and I want people to be able to find this. So that's the only reason that on Rumble, if I could have it unmonetized and also have people be able to find it, I would pick that option. But I have to choose between those 2, and I prefer to have people be able to find it. I'm not gonna upload. Oh, fuck off, Rumble. Leave page. Okay, but anyway, what I was going to say with Odyssey is that Odyssey has a paywalling feature, and what I was going to say about that is one way to really hurt my case would be to solve the exercises. And because if there are solutions to the exercises out there, then that does undermine the market value of the book because it makes it less valuable to somebody who wants to use it as a course textbook. And so I was going to say, well, my solution to that would be to paywall solving the exercises. And so that way, if you want to cheat on your homework, you have to pay me. And now this made sense when I thought of it, and now that I'm explaining it out loud, it doesn't make sense. My idea was basically, Odyssey has a paywalling feature, and I was going to test that by solving exercises, but now that I say it out loud, it doesn't make any sense. I don't know. Maybe I'll do that. I'll let people know. Anyway, how long have I been talking and not reading? Let's see. I don't have my mouse, so 12 minutes. Okay, let's get to reading. This is a pretty short section, but it's sort of the core, and the pointer better work, or I'm going to lose my mind. Sometimes it doesn't work. Okay, it works. All right, let's go through, and you know the drill. We are going to highlight some terms. So I'm now reframing this to read-along video. So I think we were talking about copyright just a minute ago. I think the best analogy is video game streaming, because it's oftentimes if you're playing, especially like a difficult puzzle game, you want to go. It's like having a solution video to a difficult puzzle game, so people can go figure out how to solve it. And reading a textbook, it's kind of like solving a difficult puzzle. Anyway, blow it up. Nope, that's too big. I can't read it. Or I can't scan. Okay, normal. We know what normal, a quotient group. I kind of know, I do know what that means. I've talking about it constantly. Here's new notation. G mod n. Canonical map, I know this. This is talking about the fundamental theorem of homomorphisms. A product set. Did we already go over this? No, this is the new thing. Okay. Oh, that's right. This is the glowy terminology again. Anyway, we'll get to this. Just scanning for terms, and then we'll go back and scan for backward references, and then go. Let's see. This is really important. This first isomorphism theorem. They call that bullshit with polynomials the fundamental theorem of algebra. That's total bullshit. This is the fundamental theorem of algebra. That bullshit about how polynomials have a root. First of all, there's no actual proof of that fundamental theorem. strange that it's called a theorem. Go watch Wildberger. He's talked about this a lot. Anyway, this is the first isomorphism theorem. Don't give me that bullshit about the winding numbers and all that. That's a bunch of fucking CIA gobbledygook. That's not a real proof. Okay, a real proof is a function where you give me a polynomial and I can give you a root. There's no proof like that. In fact, there can't be. So, the fundamental theorem of algebra is that's some weird CIA nonsense that I really just have no interest in. This is the real fundamental theorem of algebra, this theorem, this graph specifically. And the thumbnail of the video is almost certainly going to be this image. That is the fundamental theorem of algebra, not that glowy nonsense. Anyway, okay, let's go and do our references. These are in blue. Okay. Let's read this backwards, and then we'll be at the top. Lemma 212.5. Okay, but why does it turn off the ruler? That is so annoying. Lemma 212. Lemma 212.5. Let's keep going. Gonna zoom out a little bit just so I can see easier. 212.7, which is just right above. 278, that's important. 212.2, that's not on the page, and so I'll. You know what, I'm not going to do references in the same section. How about that? Okay, 278. This keeps coming up a lot. It's bracket notation. Okay, we'll see. 2817. Okay. Okay, I need the bigger pointer because I keep screwing up. Why are you fucking with me, you piece of shit software? Did the Glowies make this? There's almost no software that I actually like. So, there's software that I don't notice. I only notice software when it annoys me. And so, if I notice your software, it's because it sucks. Alright, I'm sure I missed some references, but I don't see. Let's go check 2817. Where is my book? Here it is. 2817. 2817. This is. I have a bunch of highlights around this. This is on page 59. And it looks really complicated. It has a bunch of bullet points. I'm sure we read it. Okay, now I gotta blow it up so that I can write. Come on. Page 59. It's equivalent conditions for when a subgroup is normal. That's what it is. 278. This is this is page 54. And it's a natural surjective map It's the map from a set to its equivalence classes. Projective map, projection, from a set to its equivalence classes. Which I assume, I mean, it's kind of, if you know what we're going to be talking about, it's easy to see why that would come up. And I think 278, yeah, same. Equivalence classes. And this was page 54. Did we have anything else? Lemma 212.5. Should I? Because that's like 2 pages ago. That's the only thing. 212.5. Might as well. It's not going to hurt anyone. That's 67. And it is multiplication of cosets, which is a glowy idea. Anyway, okay. Alright, let's get reading. I don't have a mouse today because my mouse is like 10 years old and I've never once changed the batteries. And so, I mean, it has a battery life now of like 2 minutes. Anyway, so in this section we show that a law of composition can be defined on the set of cosets of a normal subgroup, I guess that normal part is important, of any group G. Now, I worked out once why the subgroup had to be normal. And I think it's because otherwise the resulting thing when you quotient isn't a group. And I don't remember the example I came up with. I think he talked about an example before. Anyway. Yeah, the quotient group. Addition of congruence classes of integers mod n is an example of the quotient construction. I need my glasses. Okay, addition of congruence classes of integers mod n is an example of the quote correct. Another familiar example is addition of CIA angles. Angles don't exist. They're a CIA psyop. But I understand what he means. Every real number represents an angle, and 2 real numbers represent the same angle if they differ by an integer multiple of 2 pi. The group n of integer multiples of 2 pi is a subgroup of the additive group R plus, CIA glowy notation, of real numbers, and angles correspond naturally, I lost my place, to additive cosets, theta plus right. The group of angles is the quotient group whose elements are the code correct. The set of cosets of a normal subgroup n of a group G is denoted by G mod n. Right, so an example of this notation we've already seen is Z mod 2Z. Right. When we regard a coset C as an element of the set of cosets, the bracket notation C may be used. If C is equal to AN, we may also use the bar notation to denote the element bracket C. What? Okay, this is just dumb notation. Okay. This notation sucks. Okay. So, this means is a coset. bar means equivalence class of. Okay, equivalence class of. Oh my god, this notation sucks. Anyway, doesn't matter. Denote, because, I mean, Jesus Christ. Anyway, let n be a normal subgroup of a group G, and let G bar, right, the normal subgroup gives an equivalence, any group will give an equivalence relation, I think. I gotta think about that. I don't know. But let n be, let's just focus for now. Let n be a normal subgroup of the group G, and let G bar denote the set of cosets of n and G. There is a law of composition on G bar that makes this set into a group, such that the projection map defined by pi of a, that maps everything to its equivalence class, we just saw this, is a surjective homomorphism whose kernel is n. Sure, yeah. Okay, the map pi is often referred to as the canonical map. I call it projection. That's, I think, where pi comes from. Projection means surjection in math. They are synonyms. The map pi is often referred to as the canonical map from G to G bar. The word canonical indicates that this is the only map that we might reasonably be talking about. The next corollary is very simple, but it is important enough to single out. I got the chinken pox, I think. I'm going to put my book behind me. Let n be a normal subgroup of a group G, and let G bar denote the set of cosets of n in G. Oh boy, I am not alert enough to be doing this. Oh well. Let pi from G to G bar be the... So he didn't really have a proof of this. I guess... he has a proof down here. Okay. So, let n be a normal subgroup of the group G, and let G bar denote the set of cosets of n in G. Okay. Let pi be the canonical homomorphism. So what this means... Okay, so if we're taking... up here, we're talking about Z to, let's say, Z mod 4Z, okay? This is just mapping, like 7 maps to the equivalence class. Well, it would be 3, 7, minus 1, anything that is 3 mod 4 is 7. Does that make sense? 3, 7, minus 1, minus 5, 11, not 11. Yes, 11 is equal to 3. Yeah, it is. 11, 15, etc. Anything that is equal to 3 mod 4. That's what is meant by this map. That's just a simple example. So let n be a normal subgroup of the group G, and let G bar denote the set of cosets of n in G. Let pi be the canonical homomorphism, so this thing. Let A1 to AK be elements of G such that the product is in N. Then... Okay, so let me give you an example. what this is saying in our example up here. So let me take an example of, okay, if I take 7 plus 1, this is in 4 times z, right? Because it's equal to 8. It's in 4z. If I then look at the equivalence class of 7 plus the equivalence class of 1, because here he's using multiplication notation, but up here we're talking about addition notation. This is equal to the class of 0. Correct? Because it's 8, which is 0 mod 4. Let P be A1 up to AK. Then P is in N. P is in N. Yes. Yeah, it's obvious. I don't need a proof of this, but sure. Yeah, okay. So, I'm going to keep the book open. 66 is the 212, 2. Okay, and that way I don't have to flip back and forth. So 66. Got mucus. I don't understand. I drink my bleach. Anyway. There are several things to be done. 212, 2. Okay. This is kind of just such a trivial thing to prove that it's hard. Okay, define a law of composition on G-bar, prove that the law makes G-bar into a group, prove that pi is a surjective homomorphism, and prove that the kernel of pi is n. Okay, this is such a trivial thing. Anyway, how long does this proof? This is half a page. Okay, this shouldn't be too difficult. I have the words "fuck you" written on my... Oh, it's because of the glowy notation. See, AJ from 3 years ago was smart. He understood what the CIA was up to. Didn't know it was the CIA, though. Anyway, he doesn't have the QED symbol anywhere. Anyway, so we use the following notation. If A and B are subsets of a group G, then AB denotes a set of products. Okay, this product set. That's why I wrote fuck you. Okay, that makes sense. I literally right here in my physical copy of the book, I literally right here wrote the words fuck you. Lemma 212.5. Let n be a normal subgroup of a group G, and AN and BN be cosets of n. The product set is also a coset. It is equal to the coset ABN. I need to take a shower, and because my... Anyway. Let n... Oh, you know what? I was messing with the audio, and so the audio for this might be totally fucked up, and if it is, I'm sorry about that. Oh, no, I didn't mess with the audio. But it is too loud. Let me go check. Fucking pulse audio. Leonard Pottering is the worst person in human history. He is a worse person, I'm going to say this without a hint of irony. Leonard Pottering has done more damage to humanity than Adolf Hitler ever did. Without any doubt. Should I... It just... Okay. I'm just going to leave it. Hopefully the audio is not too bad. I am going to add my God, there's so much noise. I don't even hear it on my own. Okay. Cancel. Okay. Okay, now what is going on? Okay, since it's double recording, I'm going to mute the microphone, okay? Hopefully, Leonard, you asshole. Why is he like this? Is it applying some filter that boosts my audio? No, it's not. Leonard. I'm sorry. I should have been more alert about Leonard's bullshit. Hopefully the audio for this isn't totally fucked up, but if it is, I'm sorry. I was playing with the filters earlier. I'm not going to play with the filters live. Okay. Sorry if the audio is fucked up, and if the audio is fucked up, then I'm going to upload it with no audio. Because, I mean the audio is... Fuck this. Let me just keep going. I'm in the middle of something. Fuck Leonard Pottering. You can tell Leonard Pottering software sucks because I notice it. And you can tell Linus Torvalds software, despite what Terry Davis says, Linus Torvalds software is excellent because I never ever notice it. I'm never even conscious of the fact that I use Linux. It just works. The same with i3, I never even notice it. It just works. And never gives me any bullshit. The one thing I do notice is the X11 copy and paste has some weird bugs in it. Let me scroll up. Okay, we're here. This lemma 212.5. Let n be a normal size. Okay, okay, so we're proving this one, defining a law of composition. Okay. And the product set is also a coset, right? Because okay, so there's a couple ways you can do this. Okay. Let me explain what's going on here, and not this CIA bullshit right here. This is fuck off CIA. Let me write that. Fuck off CIA. Chloe's. Fuck off, Chloe. Let me just show you what's going on. So, let me just write out, this is always a good idea in math, is to write out exactly what everything is. So what is A times N? This is the set of AN where N is in N. A is fixed. Okay? A and G is fixed. AN is a set of AN for N and N. Bn, right. A and B are subsets. Sets. That's important. Okay, so, okay, and Bn, B, let's call it n prime, where n prime is, of course, a subgroup of G, which is fixed. Okay, and we're proving 212.5. Let me just write this out. And this is AA32 notes. Okay. Where n prime is in n, close brace. Okay, and so an bn is equal to the set of all an bn prime, where n and n prime come from n. Okay? However, a and b, first of all, I can rewrite this. Each a and b I can rewrite as ab here's an easier way. B inverse n b n prime. Okay? Where n and n prime come from n, and of course b is fixed. B and a are fixed. Okay. All I did was insert something that collapses to the identity. However, B inverse NB, where n is in n, is going to be AB times B inverse NB. That's just going to, by the definition of normality, this is some other element in n. So this is called the set of all B inverse NB, where n ranges over all of n, is literally just going to be, let me call it n squiggle n prime, where n squiggle ranges over n, because, right, when you do this, ranges over all of n, and of course n prime is in n. Okay, I'm just doing, okay, but if I take the two products of elements of n, so if I take, n prime and act on it by n squiggle, or equivalently take all of the n squiggles and act on it by all of the n primes, it's an automorphism of n. And so I just get, this is a set of all AB n n star, let's say, n star. Okay. Where n star is in n. Okay. That's it. Okay, so right, that's what it means by it is equal to the coset. It is equal to the coset ABN. It's this logic over here. Okay, and let me save. Okay, and yeah, okay. This formal manipulation, I'm going to put that in glowy green. Formal manipulation. Look at this shit. Okay. This lemma allows us to define multiplication on the set. G is G. Oh, maybe let me go back and explain specifically what this notation means. So, let me maybe give examples of this. So this would be in parallel in blue. I'm going to do 3 plus 4z. Oops. 4z. So we're doing our example in z mod 4z. Okay. 3 plus 4z plus, because this is an additive group, I don't know, 2 plus 4z. Okay? What this means is, the set of all, this one, is the set of all 3 plus 4 plus k times 4, where k is in C. Okay? And this is equal to the set of all plus the set of all. This is a different plus operation, so maybe let me double stroke this plus. Plus as in this is a set plus, so this is a different operation. 2 plus 4 k times 4, let me not use k, let me call it 2 plus, I don't know, what's another number, L. L times 4, where L is an integer. Okay, that's all that's going on here. Okay, and this operation is defined by definition, this is 3 plus 4k plus 2 plus 4l, where k and l are now integers. That's the definition. Okay, so that is, let me number these steps. Okay, so this is step 1, this is step 2, this is step 3, 4, 5, 6, and now we have a reference. So here is, this is me doing, let me just use the other color. This is step 1, this is step 2. This here, where I'm just expanding out the definition, this is step 3, so you can just visually scan which step is which. Okay, in step 4, let's do step 4. This is equal to, well, what I'm going to do is I'm going to rewrite this as 3 plus 2 minus 2. Right, I'm just adding in an identity, plus 4 times k, plus 2, plus 4 times L, where of course k and L are integers. Okay. That's the step, which is unnecessary when we're talking about a commutative situation, but over here it's absolutely necessary because we don't have commutativity. Okay, and this is of course equal to, well, 3 plus 2. I can do associativity in a group. I can't do commutativity in an arbitrary group. Okay, 3 plus 2 plus minus 2 plus 4k, okay, plus 2. Okay, so I shift to the right and shift to the left, and in the abelian situation, they just cancel out and do literally nothing. In the non-commutative situation, it might do a shuffle, okay? Plus 4l, where k and l are integers. Okay? So, this is, okay, now let's do 5. This is step 5. So, these are our n squiggles in here. Okay, this is the step where we rewrite n as n squiggles. Okay, so instead this, just to kind of illustrate what's going on, let's call this step 4.5, because it's kind of showing how you get from 4 to 5. This is step 4.5. 4.5. Okay, step 5 would be where we rewrite this as 3 plus 2, keeping that, okay, plus 4 times, so these minus 2 plus 4k plus 2, I'm going to rewrite that as 4j just to emphasize that it's different, plus 4l, where of course j and l, this is our, so the morphism from n to n squiggle, let's analogize that with k becoming j. Okay, and specifically, what I mean is when I did b inverse nb and called that n squiggle, we don't strictly need to do that step in the abelian case, but just to show by analogy, what we're doing is the minus 2 plus 4k plus 2, this is becoming 4 times j. Now, this is a silly thing to do in the abelian case, but it's a required thing to do in the non-abelian case, so that's why I'm doing it. Plus 4j plus 4l, where j and, of course, l are integers. Okay, but 4j plus 4l, that's of course also going to be you add two multiples of 4, obviously it's going to be a multiple of 4. So this is 3 plus 2 plus, okay, plus 4 m, where m is in z, okay, and and this is step 6, okay, and so by analogy, when I go from 4, let me do n tilde times n prime, this becoming n star, oh, oops, wrong type of star. When this becomes n star, that is analogized with 4j plus 4l becoming 4 times m. Okay? That's all that's going on here. Okay, and so here is a concrete example going along with the sort of more abstract ideas. This is all that's happening. And this is literally, okay, 3 plus 2 plus 4m. So all this is saying is showing the formal definition for adding 3 plus 2 mod 4. Okay? And this is how you can justify, since, well, particularly m equals minus 1 is a valid thing, this is equal to, let me switch to blue, so this is equal to 1 plus, the set of 1 plus 4 times, let me just change to a different letter in p, where p is an arbitrary integer. 1 plus 4 times p, where p is an arbitrary integer. 3 plus 2 is equal to, yeah, okay. So, by analogy, 3 plus 2 is congruent to 1 mod 4. This is the logic that would allow us to do that. This is the formal Glowy logic. This is how we get the Glowy's permission to do modular arithmetic. Alright, save. That's all that's going on here. Okay. So, I kind of lost okay, so I wrote fuck off Glowy. I remember writing that. Okay. This lemma allows us to define multiplication in our example I'm going to use pink to mean in our example in z mod 4z. Okay. Using the bracket notation, Oh my god. This notation is disgusting. Ew. I'm gonna write ew. This lemma shows that the product... Okay, yeah, sure. We just went over this. Okay. I think this product map point is kind of important. So C1, C2 is the product set. Okay. Okay. Right, the coset of A and coset of B. Right, okay, sure. This bar notation is fucking stupid. Let me write that. Bar notation is fucking stupid. Okay. Then by the definition of the map pi in 2.12.2, where is that? That's just the obvious map from any... This is like from, I think I used the example of 7 goes to 7, 7 plus or minus 4, 7 plus or minus 8, 7 plus or minus 12, etc. etc. Okay. Sure, because it works as a homomorphism. Okay, yeah. From 2.12.7, once we show the fact that pi is a homomorphism will follow from 2.12.7. Which is this. Literally, you need to number literally the equation you wrote before, not even in a previous sentence. Literally in the next sentence. Okay. This is what I was saying, is mathematicians, I think numbering equation, I get it. I get why you do it. But it's like, this is just such a fucking stupid way to know. It's literally right there. You kidding me? I can understand 278. This is great. Refer me to something concrete previously. You need to number the equation that is literally less than an inch above. Unbelievable. Okay, that's stupid. I'm giving myself an ear infection. Okay. Since the canonical map pi is surjective, okay, page 54, right, that's the definition of the canonical map, okay. Let G be a group, and let Y be a set with a law of composition, both laws written in multiplicative notation, but they're different laws. Let phi be a surjective map with the homomorphism property. Oh, this is an interesting lemma. Okay. With the homomorphism property. So if you do a... What exactly does law... This is the glowy slipping in some jargon. What exactly does law of composition? Is this a formal term? Let me go check. Because I think he means... Yep, yeah, this is a jargon term. He defines this on page 37. I think this is why I have the brace notation, is because law of composition, that could just be a... But no, this is page 30. Let me put this in... this thing where you don't mark that you have jargon, that's glowy stuff. But I'm going to put this in blue. This is page 37. Now, and all this means is a map, what means, okay, it means what I think it means, so I kind of, okay, means, I just noticed, let's go, let me show you page 37, because it's a good, my fuck you was well deserved earlier. Okay, means a map y times y to y. Now, why do I say that fuck you was well deserved? Let me show you. So earlier I wrote, or I didn't write, I wrote this in my physical book. Right here, that this, I wrote, here, let me put it in glowy green just to let the glowies know I'm talking about them. I wrote fuck you here. Now, notice this term, product set. Product set. Now, why is this fuck you well deserved? Because the page I was just referring to, where he hides jargon without, like, marking it as jargon, this is page 37, and so the book, the actual PDF pages are a little bit off. Okay. Look! The product set! He uses that term, the product set, as if it's a jargon term, whose elements? It's the Cartesian product. That's what he means. Okay, and so here was the law of composition, which, okay, anyway, let's go back to, I gotta go 12 pages ahead, so where are we? We're in 2.12. I'm just gonna find the page number by hand because I can flip the pages faster. We're at the end of page 67, or, yeah, so plus 12 would be 79. Okay. Glowies. Glowies, 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 glowies. Then y is a group, but this is an interesting idea that you can take a group and if you map it into a space that has this sort of map to itself, and then it happens to have this homomorphism property, then the target space is automatically a group. Okay, maybe a better way to think about this would be, suppose that you have a set, and you have this group, this law of composition. I'm going to use that jargon word. Okay. And if you can find another group and form a homomorphism that works with this law of composition, then automatically your new set is a group, which is really interesting. And phi is a homomorphism. That is interesting. Okay, this is right, okay. Yeah, because you can just port the group properties using the homomorphism. Right, this is the idea of a functor. This is a really important idea, which is that, well, this isn't quite a functor. This is not what a functor is, but it's the same basic idea. So a functor is a map between two categories. So let me give you an example from Haskell. Let me open up GHCI. What is going... Oh, my fucking monitor, like, reset the USB. That's what's going on. There we go. Okay. So, let me, first of all, let me blow this way up so that you can see it. This is a program called GHCI, which GHC is the Glasgow Haskell compiler, and then I means interactive. So I'm going to do :info functor. Okay, now what this is telling me, a functor is called a type class in Haskell, which is, well, it's what it sounds like. It is a class of types. And it gives some examples of instances of the functor class, and we'll talk about this in a second. Class functor, f, and what f, this is called a kind, which is sort of a castrated type. Kinds are castrated types, that's the way I think about them. Where it has two functions, fmap from a to b. This one is kind of the important one. Fmap from a to b, an f of a and an f of b. So let me just give you a really simple example. Okay, so I'm going to write in a function. So one of the examples of a functor was list. This means list. So I'm going to define x's is equal to 1, 2, 3, 4. Cool. And I'm also going to define a function called add3. Can I define functions in line? I don't remember. Add3 to x is equal to x plus 3. Does that work? Okay. Let me just try add 3 to 7. Yes, it works. Okay. What I can do with fmap, so in Haskell, think of it like Lisp, the syntax is Lisp minus parentheses. So instead of f of x, y, z, in Lisp, instead you would write f of x, y, z, and in Haskell you just write f, x, y, z. Okay? That's all it means. So what I'm going to do is fmap add 3 to x's. So add 3 converts an integer to an integer. We're given it a list of integers, and we should get back out a list of integers. And if I ask the compiler what type this is, it'll tell me, oh, because, okay. Okay. If I set, no, I have to turn some compiler flags on here. Let me do set x, what is it called? Type, no, can't remember, because what I was going to say is if I tried it, if I want to specify that I mean that this is a list of integers, it's going to give me an error. Oh, that works. And then what type is this? Yeah, it's a list of integers. Okay. Wow, okay, so they've improved GHC quite a lot since I last really did any serious Haskell. This is nice. Or maybe I have the correct extension turned on. I'm not sure. I think this is just the GHC that is installed with APT. Anyway, the point was, let's pull back up the info for a functor. Okay, let me show you the maybe data set. Let me show you what maybe means. So, whoa, that's a lot. So maybe Haskell doesn't have null like most programming languages, so in most programming languages there's a bottom value that is an allowable value in every type called null. Haskell does not have that. Instead, if you are calling, okay, let me give you an example. If I am, okay, let me give you an example, which would be, let's say I want to get the nth element of the list. Okay. Let me just show you when I would use a maybe. Okay. So I'm going to define nth. This is a standard value thing. nth element of a list, nth from my list, n, which is an integer, and my list, which is a list of anything. Okay? So first of all, I'm going to say, can I do the inline bars? You know, this doesn't matter, but let me just assume that n is greater than, because I could ask for, anyway. This is not really relevant. Okay. What I wanted to show you, okay, so, no, let me do the nth element of the list. Okay. Nth, n, which is an integer, and list, which is a list of anything. Okay. This is equal to, can I do multi-way if? I don't know. Here, I can do set dash x. This used to be a, yeah, here we go. This used to be have to be a syntax extension. Okay. So, nth, n, which is an int, and my list, which is a list of anything. Okay. This is equal to if, and then I put a bar, and this is a multi-way if. N is less than or n is less than or equal to 0. I think that's the way it works. What's the multi-way if syntax in Haskell? Let me look that up. Can't remember the syntax. Okay, it's an arrow. That's what I thought. Okay. So if n is greater... Oops. Oh, that's just... Okay. If n is greater than or equal to 0, then we are going to get nothing. Okay. If... n is greater than or equal to length of the list, then we are also getting nothing. Otherwise, so lists in Haskell, I believe, let me double check. I'm just double checking to make sure that how the listing works. Yeah, they're 0 indexed in Haskell. Okay, so what we need to do, this is a 1 indexing. So, just show you what's going on. Nth, okay. So, if we give it an invalid n, where n is greater than or equal to the length of the list, correct, nothing. Otherwise is let idx0 equal n minus 1, because n is a 1 index, in list bang bang idx0. And actually what I'm going to do is just list bang bang idx0. So the maybe type is either just or nothing. Okay? Uh-oh. Yeah, that's what I was thinking. Set. So I was saying that I was worried about the thing where I was trying to set the types in line, and I needed x scope type variables. Here we are. Okay? So, nth of, I want the second element in 1, 2, 3, 4. It'll give me just 2. But if I ask for the 11th element, there's no 11th element, so it'll say nothing. Okay, now, what I am going to do is, let me do my fmap, add 3 to just 2. It'll return just 5. And if I do it to nothing, it'll say nothing. There's another one called either, which has left and right. So if I do left 2 would be left 2. Oh, it does nothing on the left and does it on the right. And the reason is because you use left for error, because like left-handed people are the devil, that's why. And so anything like left-handed or like is just an error. And you just don't do anything with those people. You just kind of like leave them alone. And then the right, that's what you do something with. So what you would do is, like, if you have a parser that returns it that might fail, you would have left be the case where the parser had an error and the value inside of left. This is kind of like a tuple, and so in Erlang this would be like left error message or right value. In Erlang instead you would do error message or OK value. That's what you would do in Erlang. Okay? So, going back to this, I really hope my audio... I've been talking a long time, going over an hour. Okay. So, my point with this... Oh, and the maybe type, instead of nothing or just value. In Erlang, this would be maybe none or OK value. That would be what you would do in Erlang instead. I like Erlang better. I think Erlang's just a nicer language than Haskell, honestly. It's just more well done. Haskell has a lot of neat ideas. With the functor idea, I wanted to talk a little bit more about this. So this is a really crucial idea in algebraic topology, which is kind of where most of my exposure to algebra comes from, actually. And so algebraic topology is all about functors. Now let me explain. I might want this again, so I'm going to deploy it. But let me show you an example. So the way category theory works is every category has things called objects. So category theory. This is a good tangent theory. Every category has objects and morphisms. This is important. This theorem that we're going to be talking about, the fundamental theorem of homomorphism, or what does he call it? The first isomorphism. Yeah, this one. This shows up all the time in category theory. And what category theory is, it's mathematics, math, TV. It's TV tropes in math. That's what it is. And a functor is a map between categories. Is a map between categories. And you can go one level higher, which is called a natural transformation. Category theory, this is also the theory of how databases work, if you want to be a computer nerd. What do they call it? Relational algebra. It's the same thing. Okay. Called relational algebra in database theory. It's the same thing though. A natural transformation, I don't know what a functor is called in databases. Is a map between functors, I believe. I might have that wrong, so put an asterisk next to this. Asterisk. Map between functors. Okay. So let me give you an example of when this would come up. Okay, so this fundamental theorem of homomorphisms we're talking about, this comes up actually all the time in topology. So here we're talking about quotient groups, but in topology there's something called the quotient topology. And I'm not going to give a full topology lesson here. So first of all, a continuous function, I am going to give a full topology lesson, I guess. So I'm not gonna... How deep should I go? Why not? Let's go as deep as I can. So if you have a set, okay, and let's call it X, okay? A topology on X this is a term, brackets term topology. Let me do a different color for emphasize. This is a bracket term, okay? A topology on X. This is a very, very rapid introduction to topology. I'm going to switch colors and we're going to go full screen. Topology on X is a set T, and you use a curly T like this, which is a subset of 2 to the X. 2 to the X, this means, if you're not familiar, this means the power, different color, power set. Oops. Power set of X. And this 2 to the X means the set of all subsets of X. So topology is, we're doing CIA set theory. I should call this CIA topology, just to emphasize that it's a CIA psyop. Topology is more in my wheelhouse. I'm much more familiar with topology than I am with algebra. Okay, so you have a set X, sets are a CIA idea, so are topology. A topology on X is a set T, which is a subset of 2 to the X, with the following properties. Okay, number 1, the empty set and the whole space, these are both obviously subsets of X, are in the topology. So these sets in the topology are called, in topology these are called, okay, and I'm going to write this in parallel. The empty set and X are, here's a term, open sets. Okay? If what open set means that it's in the topology. That's literally all open set means. Okay? Empty set and X are open sets. Okay, and the reason I'm giving myself a little bit of room here is because some of these properties kind of get long. I need white. 2. Empty set and X are open. The empty space and the whole space are open. Okay. For any, so the way you denote this is U alpha is a subset of the topology, implies, use the double arrow for implies, the union over alpha of U sub alpha is in the topology. So what this means, let me just go to a new line. How about that? And the union of an arbitrary. Now what this means, this isn't like a glowy term, but what I mean by this is finite countable or uncountable. Okay, finite, countable, or uncountable. So doesn't matter how many sets are in here. There could be infinitely many, uncountably infinitely many. Countable, I'm not going to get into it. Look up what countable and uncountable is. I think Rudin has a section on this. Let me check. Or not Rudin. What are we reading? Artin. This would be at the end in one of the appendices. Let me check. Oops. I tore a page. Ugh. Oops. Hopefully this is my book. Does Artin talk about this? Integers. Talks about Zorn's lemma, talks about the infinite. I don't see it. I don't know, but I'm not scanning super well. Doesn't matter. I was looking in the appendix in Artin to see if he talked about this, but I don't see it. What countable versus uncountable means. So anyway, the union of an arbitrary collection of open sets is open. Okay, that's what this means. There's only 3 properties of a topology. There might be more that I'm forgetting about, but I believe there's only 3. If I have union from I equals 1. Let me actually just write it this way. U1, intersection, U2, intersection dots up to UN is open. Is in the topology. Okay, and what this means is the intersection of finitely many open sets is open. Okay? This is the basics of topology. This is what a topology is. A topology is you have a set X, you have a topology on X, and the topology is a subset of the power sets that has this property. And then if you have a pair, X, and a topology on X, this is called a, in terms, topological space. Okay? So, topology in general. Okay, and let me tell you what the so in group theory, in the category of groups, okay, I might have something wrong. Doesn't matter, this is close enough to being right, that it's close, that's true enough by analogy. So in groups, in group theory, or objects, our groups, and our morphisms are group homomorphisms, which we've talked about a lot in this playlist. In topology, our objects are topological spaces. And then there's another class called isomorphisms, which are invertible morphisms that are also morphisms. Isomorphism means invertible morphism that is itself a morphism, where the inverse is a morphism, and these are group isomorphisms. I'm not going to write out the word isomorphisms. These are topological spaces. These are our objects in the category of groups. Let me write this out. Category of groups. And a category is defined by its objects and morphisms. Okay? And a topology, the category of topological spaces. And I might have this wrong, and the reference for this would be J.P. May algebraic topology. That would be where to look. That would be where I would look to make sure, to fact check me on this, because I'm thinking that that it might be, yeah, it doesn't matter, topological spaces. Because I'm thinking that there's a slightly different category you can construct out of topological spaces. So what I was going to say is that our morphisms are continuous maps, functions. Okay, and our morphisms are continuous functions. And I haven't told you the definition of a continuous function, but I will in a second. And then our isos, these are called homeo, not homo, homeo, with an E, morphisms. And this means a continuous map. This means a continuous function with a continuous inverse, whose inverse is continuous. That is invertible. Inverse is continuous. Okay? So, what are quotient spaces in topology? That's what I really wanted to talk about. Oh, and let me tell you the definition of a continuous function. Okay. Let us suppose we have a function from f from x to y. And then x and the topology on x is a topological space. Y and the topology on y is a topological space. Okay? Then f is continuous precisely when how do I write this? For all u sub y, which means a open set in y, what I mean. For all u sub y in ty. I hate this for all bullshit, because I prefer an if then. This for all thing is a little bit. U sub y in ty implies it is continuous if the following fact is true. Implies f inverse of u sub y is in the topology on x. How do I say this in English? The preimage of every open set is open. And in high-level math, this is the definition of continuous. Okay, you've learned, if you're in high school, you learned the definition about, like, a function is continuous if you can draw it without picking up your pencil. That's that's actually a better definition than this, but, and then if you're an undergrad, you learn this epsilon delta definition, which let me try to remember it. And so the epsilon delta definition is if you have a function from R, let me tell you what the topology on R is, on the real numbers. So it is, okay. If S is a subset of R, okay, I'm going to define something called a ball of radius epsilon centered at a point x. So x is a point, and actually let me call it P. Okay? And this is the set of all points P in the real numbers such that let me just say the different how do I say this? Not P and R. Oops. This is a set of all points Q in the real numbers, such that the distance between P and Q, which I'm going to write like this, the distance between P and Q is less than epsilon. Okay? Less than a strict equality. Strict inequality. That's really important. The strict inequality is important. So these are called, these are open intervals. Okay? So these are called open intervals typically. So in particular, this would mean the open interval p minus epsilon to p plus epsilon. That's what it would mean. So on the line, if we have p here, and we're trying to visualize our number line, it's like this. Okay. A set S subset of R is open precisely when it contains the open ball centered at any of its points. And I'm not going to go into too much detail because I'm already on a ridiculous tangent. I mean, how long have I been recording? I've been going for an hour and a half. Okay. This is kind of this is an important tangent, but not strictly necessary. Okay. And so my point was going to be, if you go to a math professor and ask them to explain the definition of continuous function from real to real, like if they're teaching a basic analysis course, what they're going to remember is the topology definition. And then they're going to try to reverse engineer this one. And so what they'll always do is go, so for all, they'll go for all, it's called the epsilon delta definition. So what it is the pre-image of any set is open. They'll go, oh, they'll construct it the wrong way first and then have to backtrack and go, no, we need the epsilon first. And try it, you'll see. For all, unless they've been teaching analysis courses all the time, but if they're kind of rough. Okay, so what it would be, for all epsilon bigger than 0, this is the math definition. This is the analysis definition of continuous. For all epsilon bigger than 0, there exists a delta bigger than 0 such that let's say the distance between x and y is less than delta, implies the distance between f of x and f of y is less than epsilon. Okay? This is the analysis definition of continuous. And I may have gotten that wrong. I'm just kind of improvising. I obviously didn't plan this. And if you don't understand this, well, congratulations, you're normal. But you would want to look at Munker's topology or Rudin Principles of Mathematical Analysis. Either one of those. Munker's is a lot more wordy. Rudin is, you're going to have to do more work with Rudin. Munker's is very verbose and he explains everything with tons of examples. Rudin gives like no examples at all. And Rudin is all theory, all like just the bare minimum, but Rudin like is actually the best way to learn. So I would suggest Rudin. So if you're hardcore, do Rudin, and if you're a pussy, do Munker's. That's what I would suggest. Munker's is great. I learned from Munker's, if I'm being honest. So either one of these is very, very good. Anyway, none of this has to do with what I was talking about before, which had nothing to do with what I was talking about before that. But we're talking about this, what we're going to be talking about with this abstract algebra is this theorem, which is of the form, it's G, you have a homomorphism from G to another group, let's call it gamma, and this is our homomorphism phi. And what it's going to say is that how should we write this? Let's suppose that this is a surjective homomorphism. Okay, to gamma, which might be embedded in another group. The curly arrow the hook arrow means injective. This means injective. Injective. This means surjective. This is just standard notation that you'll see everywhere if you do high-level math. And this means bijective, because it's both. Okay? And gamma might be embedded in another group, G. Okay, and I don't want a double arrow. What I want, if it's a surjective homomorphism, what I'm going to get here is an isomorphism between the image of G between the image of phi. Let's call it, how about this? Let's formulate it this way, okay? And if you want this type of presentation, I think Lang does a good job. Lang algebra, which we'll look at, I think, does a good job of presenting it kind of more like this in more of an arrow format, arrow-based format. Okay, and let's call this the image of phi. Oh, I wanted white. The image of phi. Okay, and this is isomorphic to G mod the kernel of phi. This is, you see this theorem everywhere. There's an identical theorem in linear algebra. Okay, and then there's this, what is it called? This is a surjective map, which normally you denote by like phi bar or some faggy notation like that. And let's suppose that this is injected within some group. Okay, you get the idea. But this is called the fundamental theorem of homomorphisms, or the first, it's one of the isomorphism theorems. I think this is the one that Artin is going to call the first isomorphism theorem. Now, the reason I was rambling about category theory is you see exactly the same thing in other fields. So, you see this in linear algebra. Okay, let's suppose we have a vector space V. So in the category of vector spaces, our objects are vector spaces, and our objects or our morphisms are linear maps, and our isomorphisms are invertible linear maps. I'm not going to write that. I should write it down. Let me go write it down. I'll put it, where do I have room? I'll put it up here. Okay. Where do I have room? Okay. And then linear algebra. Category of vector spaces. Vector spaces. Okay. Our objects are vector spaces. Vector spaces, and our morphisms are linear maps. And our isomorphisms are invertible linear maps. Oh, they're all invertible linear maps. I don't want to put GLN, and the reason for that I don't want to put GLN is because I'm also including infinite dimensional vector spaces. So all finite dimensional linear maps, here this is an important enough fact that it's just worth writing down out of context. All linear maps between finite dimensional vector spaces all of them are matrices. Or in other words, if you have a linear map between two finite dimensional vector spaces, you can write it as a matrix. And there is only one possible matrix you can write it as. Okay? Likewise, every matrix is a linear map. And it is a unique linear map. Okay. We will talk about this, I believe, in chapter 4 of Artin. So maybe that's a preview. Okay? What I was going to talk about, you have this exact same theorem down here in linear algebra. So a vector space, so you have a surjective linear map. Let's call it matrix M, and this is the image of M. Okay, and then this vector space down here is, there's an implied surjection to V mod the kernel of M, and it's a little bit easier to draw this, and I'll give actually a concrete example over here. This will be nice. Because vector space is also, there's an additive group, there's an additive abelian group on the vectors. So this will actually be a nice example of the theorem we're about to talk about. And this is isomorphic to the image, okay? And then this might be, I don't know, W, which is the image is embedded. And embedding means an isomorphic or an injective map. Doesn't matter. Okay, and so let me just give you a really simple example of this. This is an example that will show up in when we do SVD in the data mining playlist. This is literally what we're going to be doing. Is this theorem? Well, this is coming up as a preview. Okay. So let's suppose I have a three-dimensional space. Okay. So this is my X, this is my Y, and right-hand rule. This is Z out here. I was right about that. Okay. And this is R3. And I'm going to form a map from this to R2 in green, in different color. Just the two-dimensional plane. And to do that, I'm just deleting the Z coordinate. Okay? This is R2 with X and Y. Okay? The matrix for this map, by the way, I said everything is a matrix. Now, it depends on whether you have it act on the left or on the right. The theory is symmetric either way, and I meant to talk more just about getting you familiar with matrices, but it's going to be a 3x2 matrix, so X, Y, Z. Okay? Okay. And it will just be 1, 0, 1, 0, 1, 0, 0. Okay? And if you do the matrix multiplication, practice your matrix multiplication. Hey, this is just X, Y. Okay? That's what I mean by every linear map is matrix. Right away, I can just define it as a linear map. Okay, the kernel of this linear map, obviously, is everything of the form 0, 0, Z, where Z is a real number. Okay? And what I'm saying, this is a trivial example, but the image of the linear map is isomorphic to the quotient of R3 against the kernel of the linear map. Okay, it's not, think about it visually. So what the quotient would mean is the equivalence class of like, the glowy way of thinking about it is like the equivalence class of planes. Okay, so these points are considered equal in the quotient space, right? But that's all that's happening. So this point here and this point here would map down to the same point down here, right? So the equivalence class, if you pick a point here and you pull it back, pick a point here and pull it back, it will map to a line that's parallel to the z-axis. Correct? So in a way, the lines parallel to the z-axis are they're the fibers of the map. That's the way to think about this. Anyway, this is the linear algebra version. The topology version, the reason I was telling you about the topology version, we can define, if we have a continuous map, you have exactly the same theorem in topology. So you have X, you have a continuous surjective map. That's important. Let's call it F, which is a continuous surjective map, and we'll just call it the image of F. And then how does it work in topology? Because you don't typically think of it this way, because there isn't a notion of a kernel really in topology, because there isn't a okay. I made a mistake. Okay, so I was right over here when I was hesitant. Okay, at least I taught you some topology. I think in the category of topological spaces, you do need these to be, Let's forget topology for a moment. Maybe we will look at May's algebraic topology, because I realized that there's not really a notion of a kernel of a continuous function. You do have the thing where you we just talked about a theorem like an hour ago. It was one of these little lemmas, which was that if you have if you have a law of composition, it was 212.8. If you have a law of composition and you can pull it back via a homomorphically looking map to a group, then it's a group. So there's a very similar situation in topology, where if you have a function, let me just show you. Okay, forget about this because I'm a little bit concerned. I think I made a mistake. So go read May and Munkers and all of those, because I'm rusty. You also maybe want to look at Hatcher. Hatcher is very verbose. What's it called? Maudlin, I think is his name. Maunder. Those two books for algebraic topology might be good references. What was the other thing? Oh, and then Greenberg, I think. Greenberg and May really emphasize the categorical aspects to it, and Hatcher and Maunder are more just trying to explain what's going on. And I think I made a mistake, because I think what I did wrong is that this is not the category of topological spaces. I think instead you need these to be homotopies. The morphisms are homotopies, and your isomorphisms. Yeah, so you need the whole theory of topology in order to have a well-defined definition of continuous functions. And then on top of that, you need some specific type of continuous functions called homotopies. Let me just write that term so that you hear it. Homotopies. Which are the generalization of continuous paths. Continuous paths. Okay? So you need homotopies, which are the generalization of the idea of a continuous path. And I think that is where you get the category from. And I think I made a mistake. Anyway, but there is something called the quotient topology, which is related to the quotient group idea. And in fact, oftentimes you get quotient topologies by taking a topological space and quotienting it by a group, and then that implied map here, so what you would do is actually just quotient, you have a group acting on a space. So an example would be, let's say you have the additive group on the vectors, the two-dimensional vectors with the additive group structure of R2, and you quotient out by Z2. So what you say is that I don't care, I am pretending that 2 points are equal if they're an integer distance apart. Likewise with like Z mod 4Z, we're saying I am considering 2 points to be equal if they differ by a multiple of 4. I am saying that 2 points in the plane are equal if they differ by an integer. If they differ by an integer coordinate. So this is not only equal to this, but it's also equal to this, and so we're like considering like kind of this transformation family of lattices, if that kind of makes sense. But anyway, the structure that you get when you do that quotient gives you a torus. And if you don't believe me, I can't ever remember the right way to draw a torus. And if you don't believe me, what you do is you take a sheet of paper and you fold these two sides together like this, long way like that. Fold a piece of paper, and that way you get a, when you do that, you're going to get a cylinder. So, cylinder, which is, by the way, R2 mod Z. That's the cylinder. That's the definition in math of a cylinder. Okay. Okay, here would be the way you would construct it. You would take R2 mod Z2, okay, and you define the map using the group theory projective map, okay, and then you fold these other two sides, and then that way you get a torus. Just do it with a piece of paper, and that's how you get a torus. You define this map from the group theory projective map that you get, that we're just going to talk, that pi map that we were talking about, the 2.7.8 pi map. That's that map. Okay? And then what you do in topology, the quotient topology, is the implied topology on this new space, and you define that by defining pi to be continuous. And this is a wonderful glowy trick, and that's why I'm writing it in green. So pi, in this case, would be from R2 to the torus, continuous. Now, what do I mean by that? What that means is you define the quotient topology. Look that up in Munkers is the right way. Munkers is the only book that would talk about this. You define the quotient topology. Let's call it. This is glowy green, so we get to use this notation: t sub t, curly t sub normal t, as being equal to. How do we say this? Curly t sub t. Actually, I'm going to keep that there. Defined by, okay, a set U sub t, which is a subset of t, or equivalently, this means it's in the power set 2 to the t. U sub t is in the topology on t precisely when pi inverse of U sub t is in the topology on R2. So, what this means, well, by definition, what you're doing is you're defining the quotient topology to be the most minimal topology possible on the target space, such that the projection map that we get from group theory, is continuous. So think about this. Go work through the details if you don't believe me. Quotient topology. This is a really common way of constructing new spaces. The quotient topology, and then that way, this gives us a topology on the torus. Okay, that was a fun diversion, but that's what quotient topology means, and that's what quotienting means in topology. It means, well, we're kind of hinting at the idea here, which is you have some set down below, which is y, and it had in this case it has the associativity, the law of composition operation, and if you can, and the surjective part is important, and that way you don't get stupid things happening. That's why. The surjective part is important. So the topology version of this would be you define yeah, it doesn't quite, I see why he structured it this way. Because you can't just pull back an arbitrary map and define it to be a homomorphism. Because you would have to check that the kernel of it is normal. And that's not guaranteed. Well, it is true that the kernel of every homomorphism is a normal subgroup. But I don't think you can just do the thing where you define any... Like here, in topology, you can literally just do a trick where you define a map to be continuous by changing the definition of continuous, changing the topology, defining the topology on the target space so that some arbitrary function is continuous. You can do that in topology. That's a perfectly valid and useful trick to do. I don't know if you can do that in group theory. That's an interesting question. And I think this is kind of the lemma which says, you can kind of do that in group theory. This is a lot of glowy bullshit anyway, so I don't think this really matters. Because you can't compute, none of this is the topology is completely uncomputable. So it doesn't really matter as far as my mission, which is Q-anal. But this is kind of interesting aside. Anyway. Okay, the proof is that you port the group axioms. Alright, I am out of steam. How long have I been talking? I've been talking for quite a while. Wow, if the audio for this is fucked up. Oh boy. 2 hours, 3 minutes. You see why I always check the audio at the beginning? Am I recording with the right microphone? And I do that so often I didn't even notice that it got fucked up. So I just kind of, I guess, saw the waveform dancing and didn't double check. 2 hours. Alright. Let's finish up. We're almost done now, right? Oh boy. Okay. So, here is the end of the proof of 2.12. The only thing remaining to be verified is that the kernel of the homomorphism pi is the subgroup N. Well, yeah, sure. Okay, this argument makes sense. Read it. I'm done talking now, so I want to stop. Let's just keep. This makes sense. Okay, let me just read it out loud. The only thing remaining to be verified is that the kernel of the homomorphism pi is in the subgroup N, while pi of A is equal to pi of 1 if and only if A bar is equal to 1 bar, or the coset AN is equal to the coset 1N, and this is true if and only if A is an element of N. Done. That's obvious. Here's this schematic diagram. This schematic diagram sucks. The torus diagram is much better. Or like a clock, right? Maybe, I don't know. Fine. This diagram is fine. but it means like partitioning. This is not like a plausible way that the geometry would actually work. Think about a clock, and you think about. Here's what I'm going to do. How many colors do I have? Okay. I'm going to use red, blue, pink, and orange. Okay? Better way to think about coset multiplication is that this is z mod 4z, and over here is, let me draw a straight line. I can use the ruler. Here would be z, oops. Here would be z, our modular arithmetic is clock arithmetic, that's why I drew it in a circle. And it would be alternating. It would be red. So this coset thing is like coloring points. Red, green, pink, orange, red, let me just do one more. And how about orange over here? Here, I'll go all the way either way. Pink, and then pink is followed by blue, and then let me give them numbers. This is 0, 1, 2, 3, 4, 5, 6, -1, -2, and -3, and this gets mapped to the class of 0, the class of 1. Oh wait, no, Artin is using the bar notation. I'm writing in glowy green, so I might as well use the glowy notation. 0 bar, this is 1 bar, this is 2 bar, this is 3 bar. Okay, so everything that's equal to 3 mod 4 is in orange, everything that's equal to 2 mod 4 is one of the purple points, and everything that's equal to 1 mod 4 is one of the blue points. That's the idea. Okay? So, alright. Our assumption that n be a normal subgroup, yeah. Okay, if H is not normal, this is important. Let me put the star next to it to signal that it's important. Okay. I know what this was a question I was asking earlier, which is I said at one point I worked out what happens if the group is not normal. And this paragraph. So let me just do this. This paragraph. I worked out what happens if the group is not normal, and I don't remember what I worked out. And by worked out, I mean like years ago I figured it out. And now he's answering the question. Okay. Reminding people of caveats. See, that's I think what Rudin's trick is he doesn't mention the caveats to you. I was mentioning Rudin is my favorite math author. I think Rudin's trick is he doesn't mention the caveats, but he structures his exposition such that if you don't figure out the caveats yourself, you're gonna get really tripped up. I think that's really what it is. Rudin does not explain the caveats. He doesn't point them out. He structures his explanation such that if you don't figure out the caveats, you're gonna get all tripped up. And then you discover the caveats by getting tripped up and figuring out what the fuck just happened. That's really how Rudin works, I think. And that's really how you learn the caveats of the theory. You're going to learn a lot better by getting tripped up and having to figure it out yourself than by just reading it in a sentence, because you read it in a sentence, you just forget. Right, I'm not going to remember this paragraph. I would remember if I didn't realize that the normal thing was important and got tripped up by not realizing that anyway. Rudin's great. Artin, I'm really liking Artin a lot more the more I read this. Anyway. So, if H is not normal... Okay. there will be left cosets C1 and C2 of H. Right, so not normal. So normal would mean that the product of two cosets is a coset. Or that the product of two... Normal would mean that the product of any pair of left cosets is a left coset. Not normal, by negation, by the definition of negation, means there exists a pair of left cosets such that their product is not a left coset. Maybe I should write that down. I'm tired of writing, but I think this is important enough to write. Okay, so normal I hate green. I like blue. Let's do blue. Normal means for the product of any pair. Any means all in math, which is dumb. The product of all. No, I like any better. Of any pair that's an important point. I'm going to write this in glowy green because it's a glowy term point. Any means all in math. Okay, the product of any pair of left is a left coset. Okay? And then the opposite of normal, of course, is queer. Okay? Okay. Okay, a coset is queer, okay, if there exists a pair, if there exists queer subgroup. Okay, a queer subgroup means there exists a pair. That's a good color for queers. There exists a pair of left cosets where the product is not a left coset. There exists a pair of left cosets where their product is not a left coset. Okay? The product of any pair of left cosets is a left coset. So there exists a pair of left cosets where their product is not a left coset. And you can't form a group by modding out queers. Okay. Moduloing by a normal subgroup is how you get a new normal subgroup. You can't... How about instead of quotienting, we call it marginalizing? That's the point. You can't produce a new group with queers. Can't reproduce. Maybe that would be the lesson. I don't know, something like that. I like this normal versus queer distinction. That's hilarious. Anyway, what am I doing? Let me save. See, it takes forever to save and slows down my machine. Probably fucks up the frame rate of the video. Okay. This is going to take forever to process. I might have to split this up into parts, and I really hope the audio didn't get fucked up. That would suck. Anyway. Even if there's no audio for this, I'm still going to upload it. Alright. Okay, so he's using the example y of S3. The product set yx 1h times xh contains 4 elements. I'm not going to verify that. It is not a coset. The subgroup H is queer. Okay. The next theorem relates the quotient group construction to general group homomorphisms and provides a fundamental method of identifying quotient groups. Okay, first isomorphism theorem, which this is really the fundamental theorem of algebra, not the polynomial thing. Let phi from G to G prime be a surjective group homomorphism with kernel n. The quotient group G to G mod n is isomorphic to the image G prime. Yeah, this is what I just wrote. To be precise, let pi from G to G prime be the canonical map, or G to G bar be the canonical map. There is a unique, that's interesting, unique canonical isomorphism, and then it has to be surjective. I remembered that. And so every map is surjective onto its image, and that's what I was doing back here with this thing. You can from any homomorphism pull out a surjective homomorphism. By, let's say we had a homomorphism from G to gamma, then I can just call it a different homomorphism from G to the image of the first homomorphism. Okay, and then say, oh, well, this is a subgroup that's embedded in the group, so I can form an isomorphism. Can I do that? Or I can do a homomorphism from the image into the group. This is all glowy shit, so it's not supposed to make sense. But anyway. Unique isomorphism. Such that the that's the key property, is that these that's right, I forgot about that. These are called commutative diagrams. Look that up. Look that up. That's important. Commutative diagrams. Yeah, so that if I go this way, there's only a single homomorphism, isomorphism. Let me zoom way in. Okay, and for the thumbnail, I've been doing a thing in the last video where I do the thumbnail. I think I will pick. I might like figure out a way, like something like this. Commutative diagrams, go look that up. There's a unique isomorphism from G bar to G prime, right, such that this is called the diagram commutes. This is the phrase, the diagram commutes. Which means it doesn't matter if I go this way or if I go this way, I get the same result. Proof. Ooh. Oh my god, I still have another page. Oh god, okay. The elements of G bar are the cosets of n, and they are also fibers of the map phi. 2, 7, 15. Oh god. This up. For fuck's sake. 2, 7, 15. 2, 7 is equivalence, relations, and partitions. 2, 7, 15. It's the last, it's page 56. And it was just what I was talking about, how you get equivalence classes from fibers of a map. Okay. The map referred to in the theorem is the one that sends a non-empty fiber to its image. Oh my god. What is it? I really don't want to read the proof. The map phi referred to in the theorem phi, okay, this is phi bar. phi bar referred to in the theorem is the one that sends, okay, so G bar are the coset, the elements of G bar are the cosets of n, and they are fibers of the map. They are also the fibers of the map phi. Okay. The map phi bar is the one that sends a non-empty fiber to its... okay. Oh, God damn it. One that sends a non-empty fiber to its image. Okay. That makes sense. For any surjective map of sets, one can form the set G bar of fibers, and then one obtains a diagram as above, in which one get for any surjective map. Yes, okay. And then one obtains the diagram. Okay, yeah, sure. Diagram as above is the bijective map. Yeah, right, because obviously there's a bijective map between fibers and points in the image. That's a definition of fibers. Yes. Yeah, and so this phi bar is an isomorphism because it's just one half of the obvious relationship between fibers and points in the image. Right, okay, that's why it's canonical. Yeah, that's why phi bar is canonical. It is the obvious map between fibers and points in the image. Right? Duh. The George Floyd level obvious map. So when phi is a group homomorphism, phi bar is an isomorphism, because phi bar oh my god. Oh, I know why I have so much stamina. I just took off my glasses and my eyes are bleeding and I can't read. Now if the glasses give me super stamina. When phi is a group homomorphism, phi bar is an isomorphism, because why? Because phi bar of the equivalence class of AB, so the fiber of AB, is, yeah, right, it's equal to phi of AB, which is phi of A times phi of B, which is phi bar of A bar. I'm going to put a there, because I don't see why that proves it's an isomorphism, and I'm too tired. I don't see why it's an isomorphism. Okay, anyway. Let G from G prime, I'll put a circle back to this. I don't see why ISO. And then red for come back to this. Okay. And let me highlight it in red, because I'm not. God damn it. Fucking. Why doesn't it save my setting? For I'm using the highlighter. I want it to have the ruler. If I'm not using the highlighter, I don't want the ruler. It's very simple. I should never notice your software, ever. If I notice your software, it's because your software sucks. Okay. Okay. Group homomorphism with kernel N and image H prime. Right. Yeah, this is what I just said about how you can make any homomorphism surjective by pretending that its target space is its image. Right. Yeah, I don't need. Yeah. Two quick examples. The image of the absolute value map is the group of positive real numbers, and its kernel. Image of the absolute. This means non-zero complex numbers. Okay, I was getting hung up. Okay. Yes, that's correct. Yes. And let me switch to a different color. Yes. And its kernel is the unit circle. Right, yes. The theorem is group. It's a multiplicative group, right? Multiplicative group. The image, okay. The theorem asserts that the quotient group is isomorphic. Oh, right. Okay. Yes. So what this is saying is that if you ignore rotations in the complex plane, then you basically have the positive real numbers. And topologically, if we did our topology trick, we would say that they're that the complex numbers and the non-zero complex numbers, you factor out the rotations, you get the you factor out the rotations, which are the unit circle, you get the basically the positive real numbers, because the only thing left is its absolute value. The determinant is a surjective homomorphism whose kernel is the special linear group. So the quotient, yeah, SLN is normal because it's the quotient of a... This is really interesting. Okay. Yeah, duh. But the quotient, SLN is a normal subgroup of GLN because, duh, it's a how was it surject? Because you can construct a matrix with any possible determinant, right? Just put a diagonal matrix with ones in all of the entries except for the top left one, and there you can get arbitrary determinant you want, whose kernel is a special linear group. So the quotient, GLN to SLN, is isomorphic to R star. Yeah. Wow. There are also theorems called the second and third isomorphisms theorems, although they are less important. Whew. That was a wonderful chapter. And that was the most fun I had in a section was reading 2.10, the correspondence theorem one, because that was... This I kind of already knew. The correspondence theorem was not... I had seen the theorem before in retrospect, but it wasn't obvious. This was kind of like obvious to me why it was true. We're going to get into some stuff I don't know, and that's going to be a lot of fun. We've already seen a bit of stuff that I wasn't super familiar with. Anyway, thank you for watching. If you watched all the way through, I must be pushing 3 hours now. 2.5 hours. Alright, thank you for watching if you watched. Hope you have a nice day. Good night. I really hope the audio didn't get screwed up.